Welcome everybody to the online seminar series Machine Learning Needs Mathematical Optimization. We have the pleasure of having today David Ríos Insúa, who is a research professor at the Spanish Institute of Mathematical Sciences and a member of the Spanish Royal Academy of Sciences. He is the APSARA ICMAT chair in adversarial risk analysis, and besides that, he is also a professor of statistics and operations research at the Complutense University in Madrid on leave. David has been attached to other universities such as the University of Manchester, Leeds, Purdue, Duke, and etc. His work it's mainly around decision analysis, negotiation analysis, Bayesian statistics, and today he's going to be talking about adversarial machine learning, among others. And he's the author and editor to 18 monographs, and he has edited 9 special issues, and he has more than 150 papers and reference chapters. And he has also been awarded many prizes, among others by the Decision Analysis Society and the Society for Risk Analysis. So we are extremely pleased of having today David in our online seminar series. And the floor is yours. For the audience, we have the usual way in these seminars that we will pose the questions towards the end. But if there is something very, very urgent, I will be very happy to read to David any questions that you may want to pose on the chat. Floor is yours, David.
Okay, thank you. Thanks, Dolores, and thanks the NeEDS Consortium for this invitation. So I shall talk on this. I mean, the core topic would be providing or trying to provide fast, efficient computational methods for adversarial machine learning. And in this, our focus will be on using what we call augmented probability simulation. So as you can see, the first word of the title is optimization. The last word is well, the last 2 words are machine learning. So there's a perfect matching with the purpose of your consortium, your project. So this is joint work with Tahir Ekin, who is at Texas State, Alberto Torres, who used to be a postdoc at ICMAT, but now he's initiated a startup called Comorevi, and Roy Naveiro, who is a postdoc at ICMAT as well. So as I said, the core, and Dolores also mentioned, what is the core topic is within machine learning. It's the core topic of this talk is in adversarial machine learning. And in case somebody is not aware of this area, I'm going to start with a very brief overview of it. Okay, so we start with machine learning, right? Just a simple slide. And well, there's been many successes in this area in the last few years, last decade, let's say. And probably that's the reason for which this project is going and so on. I've just put some examples from our lab. For example, this has been applied in important problems like discovery of useful molecules, or decision support in automated driving systems, or reverse engineering of personality models. These type of examples and many more that other labs and other companies are doing have given rise to an enthusiasm in this area, and there's a massive deployment of machine learning systems all over the place. But with this, a number of concerns have raised And today we're going to talk. We're going to deal with one of these, which is security, right? So our idea is that machine learning is going to meet security, and the core problem is that a traditional assumption in machine learning, which is that we are using essentially independent, identically distributed data. Well, this shall not hold because the training data and the operational data will not be the same in this adversarial machine learning context.
David, I'm not sure that we are seeing the same slide that you are commenting. Could it be that you are not on the first slide?
Yeah, I'm not on the first slide.
So maybe what we have to do is maybe you have to share in a different way because we are only. Oh yeah, now yes, yeah, yes. Now it's moving.
Okay,
yeah.
So this is I'm not full screen right now, so I will give it no full screen, right?
Okay.
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 Well, but the nice dynamics will disappear, but it's okay. So what I was saying was that machine learning needs to meet security, and I put here a little example. One example that it's typical it's a typical coursework when we deal with deep learning models. So we use a convolutional neural network to recognize handwritten numbers, and I put a sample there. And it's relatively easy to get pretty good results in this with accuracies which reach nearly 99%. So that's pretty good. The thing is that we could actually attack data. The data in this case are the images that I'm showing there, and I'm actually the images that appear below are attack data, are attacked images. Probably you won't, but if you get close to the screen, you'll see that some of the pixels are grayer than the upper part. Well, in any case, these data have been attacked, or these images have been attacked with a method called FGSM, and we completely fool the same algorithm that I mentioned before. So you can see that, for example, the first image which is a 0 to the human eye is now recognized as an 8. The second one, which is a 1, is now recognized as a 7, etc., etc., etc. And actually, the performance of such algorithm, it gets completely downgraded. So it goes from 99% to 62%. Okay, so you could think of well, that's interesting, but so what are the practical implications? So the practical implications are reflected in a scene like this. So that's aims to be like an autonomous driving car, right? Which is in front of a stop sign. The car would capture this with its sensors. It would process such information with its algorithms and the onboard computers. And it would classify this hopefully as a stop, and as a consequence, it should stop, right? It should make a halt as human being would do in such situation. But the thing is that those type of classifiers have been fooled in the sense that I just mentioned before, and slight perturbations of the images, the driving images, have been applied so as to fool the classifiers, much in the sense that I mentioned before. And some slight perturbations of the stop sign could lead to the sign actually recognized as a yield one, and rather than and as a consequence, the car rather than stopping, rather than making a halt, it would go ahead. and potentially this would lead to an accident, and that's bad. So machine learning is susceptible to attacks with potentially catastrophic consequences, and this has been reflected not only this has been reflected in critical areas. I just described one possible scenario in autonomous driving, but these kind of things have been described also in other areas like e-health, for example, when we tamper with the vision systems of a robot which takes care of patients or supports a medical doctor in taking care of patients. And it's been reported also in finance, for example, in things like insider trading. So this problem of machine learning being attackable has led to the emergence of a relatively new field, which is called adversarial machine learning. I'm going to explain you now the three core topics, the three main areas in adversarial machine learning. And I'm going to use this to make two major points. The first one is that either explicitly and sometimes just implicitly, the field is permeated by or pervaded by game theory with some and this requires some unrealistic assumptions that will motivate my discussion. And the second thing, and that this will make the consortium very happy, is that optimization ideas are all over the place in adversarial machine learning. So the first topic which is of interest is in this area is what we could call frameworks to deal with the problem globally. We'll see that this is somehow a kind of an arms race between defenders and attackers, and there's like global approaches or frameworks to the problem, and the most let's say the pioneering one is called adversarial classification. So this is a game or a competition between a classifier C and an adversary A. Suppose to simplify that there's two classes of objects that we need to classify. These are malicious and innocent. So this could be, for example, spam and ham messages, or I don't know, fraud, or legitimate internet transactions, or whatever. In its most basic setting, C and A must maximize expected utility under common knowledge assumptions, and finding Nash equilibria in this game is extremely complex, and therefore this led to this pioneer work by Dalby and his colleagues some few years ago. They proposed a scheme based just on the classifier, which is naive Bayes, in which first the classifier assumes that it's operating with clean data and finds his or her best classifier, the best parameters for the classification problem that it's facing. Then, knowing this, the adversary chooses what would be the optimal attack against such optimal classifier, and this provides this A-star optimal attack. And finally, the classifier chooses the optimal protection against such attack. This could go on and on, okay, but with these three stages is sufficient to illustrate the concepts. So there's some comments that I mean, from a, let's say, mathematical or rigorous point of view, this is a myopic approach, so it's going ahead. It's a forward myopic approach, sorry, and it's under strong common knowledge because the adversary knows a lot about the classifier, and the classifier knows a lot about the adversary, which is not realistic. Okay, but this piece of work has been ultra influential in the field, and has I mean, most people makes these pretty strong assumptions. By the way, I said game theory, and you can see here that there's lots of optimization going on in this part. So the second topic is more of a partial one, and it refers to designing attacks against machine learning systems. And one good example is our adversarial examples. And actually, the thing that I mentioned before with the handwritten digits, it was an adversarial example with what is called the fast gradient sign method, which has been, I mean, I'm almost sure that you've seen this in the media, right? So basically, this is adds purposeful adversarial noise, which to the human eye has no apparent pattern, right? You add it to an image. The resulting image is almost, I mean, it looks the same to the human eye, but the classifier, the automatic classifier that is used gets completely fooled with the security consequences that I mentioned before. I just wrote there I mean, one source of examples. There's many more, but one is the FGSM. And again, you can see first that optimizations is very relevant in designing attacks. First comment, this is just an iteration of a gradient gradient ascent, right? This is just an iteration of a gradient ascent, right? That's the first thing. Or in game theoretic terms, this is a best response to a deployed model by the defender, by the classifier. That's the first thing. And the second one is that game theory again is relevant and with a lot of common knowledge, because this type of model requires the attacker, who is the person who is noising the image, needs to know what algorithm is being used by the classifier, what type of loss function. So the attacker needs to know the loss function in this case, which is not super realistic in many cases. The third topic, which is studied in this area, is our defenses, and the most well-known is called adversarial training, and basically this consists of training the model with attack samples, and then minimize. And basically, this is minimizing empirical risk under worst case perturbation. So see, again, the two things that I mentioned. Again, we have. In this case, it's a bi-level optimization problem, which is quite complex. And the second thing is that, again, this has a game theoretic formulation, which demands a lot of information. So the attacker needs to know CD and age, etc., and that's a lot. That's a lot to ask for. So as a summary, in this sort of brief introduction to adversarial machine learning, now the field is quite popular, and you can think of everything adversarial. Any machine learning or any statistical model that you could think of, has been probably dealt either through attacks or through defenses with these kind of concepts. So you can see, for example, there's adversarial support vector machines, etc., etc. Mostly has been dealt with from the game theoretic perspective, and as I said, perhaps implicitly, not necessarily explicitly. And this requires that common knowledge is too commonly assumed, and that doesn't make much sense, at least in the security domain, from my point of view, because there's normally a lot of uncertainty about attackers and so on. It's also a quite difficult area, and it's evolving quite rapidly. As I said before, it's like there's some kind of arms race in which researchers and I don't know, armies and companies, etc., alternate periods in which there's They discover new attacks, and then they need to discover defenses against such attacks and so forth. And it's very relevant from an applied point of view, both in, for example, just to mention two, unfortunately, two very important topics in this since the last week, which are national security and cybersecurity. Okay, so I'm going to explain quite super briefly the approach that we propose, which is motivated by trying to mitigate this or replace game theory with adversarial risk analysis, with the idea of reducing these such common knowledge assumptions. And I'm putting here our initial model that we called ACRA, which is adversarial classification based on risk on adversarial risk analysis, to sort of give some kind of idea of the kind of models that we use. On the left, I'm putting here the sort of a standard, graphical description of a classification problem. So you can see here that there's an agent, the classification system, the machine learning system, that needs to make classifications based on some data X. This data X provides some information from the underlying label. So you can see this could be a spam or non-spam, or other. And so based on the data X, we need to make a decision. What type of label what type of class does this object belong to? And based on the actual class and the label that we assign, we get utility, and our idea is to maximize expected utility, right? That's sort of a compact description of a classification problem. Now, in adversarial cases, you can see that there's another agent, an attacker, which can somehow tamper the data, and so that the classifier, rather than receiving X, is receiving X prime. So the attacker is making some changes to X to try to, for example, make us believe that some email which is spam is actually ham, and make us for this, of course, this is making this with a purpose, with a benefit. So the attacker is trying to fool us to make some benefit. In the case of spam, is to make us click on a message so as to get his business, right? So that would be the sort of enlarged classification problem with an attacker. So there's a competition between two agents, each one with its own benefit, right? And we need to operate this. Now, the approach that we, in a sort of very schematic way, what we try to come out is this problem. We view the decisions. We consider these attack decisions as an uncertainty, as another uncertainty, right? And then what we have is, let's call it a standard decision analysis problem. So we would solve again, but now taking into account that we might have been attacked somehow. So as I said, this is a standard decision analysis problem. The only thing is exotic is this uncertainty, which before it was a decision by a strategic adversary. So the thing is that we need to come up with probabilities which are more difficult to assess than standard ones. And our way to come out with such probabilities is by taking into account what is the decision problem of the attacker. So we formulate the attacker problem, which is reflected on the right, right? And we try to solve this problem The thing is that we don't have the attacker available to find out what are his beliefs and preferences. So what we do is basically come out with random utilities and random probabilities for the attacker. Then we simulate from the attacker problem, and this will provide us the forecast that we need of the actions of the attacker, and then this fits in the decision, the original or the defender decision problem, and what this provides us the solution for this. There's a number of algorithms, but in a nutshell, basically, once we in operations, once we receive an instance X prime that might have been, we need to somehow estimate where this instance could come from, and what would be the original. What would be we need to estimate somehow the distribution of the original label given the received label, and based on that, we try to come out with the operation. Okay. So the crucial part is estimating this distribution of the original instance given the original label, the original features given the received features. I'm putting this example from using this kind of algorithms. This is a classification, an example in spam classification, right? And I've used here to show that this phenomenon affects or could affect basically all types of classifiers. I put here there 4 classifiers, popular classifiers used to classify spam. I put here NiPace, a logistic regression model, neural network, I believe with a couple of layers, and a random forest model. And you can see that untainted means that it's using let's call it clean data from, for example, from the UCI database. So it's doing. You can see that it does a pretty good job in classifying spam. So you can get 94% from something from around 90%. Which is quite good. The second column reflects what we could call an unprotected classifier. So an classifier which ignores. So we attack this data in some way, and we can see that by the way, that was a very simple attack, which is called one good word attack, inserting one good word attack, and you can see that the performance of these classifiers degrade considerably, right? For example, in the case of random forest, it goes from 94% to accuracy of 94% to 66%. So, and this means basically bigger opportunities for the spammer to make his business. And you can see on the right how we can recover with this classifier that I sketched, how we recover performance. So in some cases we even perform better than with the tainted, just by taking into account the uncertainty of the possible origin. So that's good news, and we made I mean quite good, I mean quite intensive experiments with this, and so we perform quite better, and with these ideas we perform better than with a standard game theoretic or a state-of-the-art game theoretic approaches to adversarial machine learning. Okay, so that's the good news. The bad news is that this takes a pretty long time, right? And so that we could think of using this for backend applications, but we need front-end applications, and this is required in, for example, in internet transactions or in automated driving systems. So if we need front-end applications, we are not there yet, and that's why that's the reason for this kind of algorithms that I shall discuss from now on. So the things that we are trying at the moment are based on something called augmented probability simulation. And for those who, well, in case there's somebody who doesn't know what is augmented probability simulation, I'm going to go super briefly through it. Okay. So augmented probability simulation is a way to find alternatives of maximum expected utility theory alternatives. So you can see that again. This conforms to the topic of the seminar. This is optimization and machine learning. So that's it. So as this is reflected here, that's the kind of problem that we try to solve. Find the alternative of maximum expected utility. U would be the utility, and P is the P of theta given X represents the posterior in a model, in a Bayesian model. And this could be super complex. I mean, this could be very high dimensional, etc., etc. This could be non-standard, right? Okay, so one possibility would be to approximate the expected utilities by Monte Carlo and then optimize the Monte Carlo sums. So basically, we would need to get a sample from the posterior, right? And then solve this nonlinear optimization problem, which would lead to an approximation of the solution. The first problem that we could think of is how would we sample from the posterior? That's a standard. That's a standard. I mean, for now is let's say let me correct this. Until let's say 5-10 years, it was a standard problem because there was MC, but now we have we still have a major problem to solve. But let's go back to 10 years ago. We could use many of the MC problems that available. And one example, and I'm explaining it because we'll mention it or we'll use it later on, would be the Metropolis-Hastings sampler. So the Metropolis-Hastings sampler, what it does is creates a Markov chain with target the posterior, and then by a simple scheme, by a relatively simple scheme, in which it provides candidates. It generates candidates, and with certain accept-reject probabilities, it would accept or reject such candidate, and this would provide this the iterations of the Markov chain. And the idea is that this, if properly designed, this Markov chain will have as a limit distribution the target distribution. Okay, so that's Metropolis-Hastings. There's in some situations you can use Gibbs, and you can use Hamiltonian Monte Carlo as well if you know some information about the gradients. But just a sort of like a KitKat moment, this worked okay until like 10 years ago, when all these deep learning things started and very large dimensional problems. There's been attempts like SG, MC, and SGLD, etc., some variants and so, but that's still a problem. There's still, I mean, the basic idea is that MC doesn't scale super well yet, and that's a problem which is quite important to be solved by somebody. But that's not the core of our discussion today. So in this example that I showed before, like this one, and it could be the case that this distribution depends as well on the action. So there's and that complicates the problem because, well, at least naively, for each action, I mean, the expensive part of the previous problem was to generate the Monte Carlo samples. That was. If we make the distribution depend on the action as well, then we would need to make this expensive step at each alternative. We could use important sampling, etc., but let's take the naive way. for a moment. So that introduces another complicated. And to solve this, that's why we introduce augmented probability simulation. So basically, what we do is we expand, we augment the probability space. Before we had the states which were theta, we augmented with alternatives, and we define a distribution which is proportional to the product of the utility and the probability. Okay, for this U needs to be non-negative, which is basically with no loss of generality. And now, so consider or dream for a minute about this distribution, right? This product of utility times the original probability. If you compute the marginal of this distribution, and I'm putting this here, if you make the marginal of this artificial distribution H on theta, you can see that this is proportional to the expected utility. So the little discovery that you have here is that the maximum posterior expected utility alternative, which is the one that you should implement, right? The one that you aim for, right? The optimal alternative is actually the mode of the marginal of this artificial distribution. Okay. So this suggests a sort of novel scheme to, let's say, stochastic optimization, or to decision making under risk or under uncertainty, which is basically the following: is first you generate a sample from the density from the artificial density h of a theta. Then, and this second step is trivial, you convert it to a sample from the marginal. So basically you just get you get rid of the thetas. And then what you need, the third step, we need to find the sample mode. So first example, we have, at least in theory, we have the technology for Markov chain Monte Carlo, which we just described. The second step is trivial, and the third step is, I mean, we could think that it's simple or trivial, but it's actually quite tricky. But luckily, there's been lots of work recently and this is a quite important topic, modal estimation. There's a very good review by Chacon, and there's a very good method in multivariate, multimodal estimation by Chen, Genovese, and Wasserman. Okay. So this is the let's call it the technology and method that we are going to apply now for adversarial machine learning and adversarial risk analysis. Okay, so we call this briefly APS-ARA, right? And basically, it's a computational method for solving games. I'm just going to discuss the version for adversarial risk analysis. So you could use it for computing Nash equilibrium. And I'm also just discussing the version for what we call defend attack problems. I shall mention in a minute. I shall detail in a minute. What are called also as well Stackelberg games. So you can use it actually for multi-stage, for sequential multi-stage games. You could also use it for simultaneous games, and you could use it for games described as general by agent or generic by agent influence diagrams. But of course, it has what is called the usual curse of dimensionality will be around, and I mean for large scale problems we would need other tools. For many stages problems we would need other tools. Okay, so I'm just gonna explain the ARA and the sequential defend attack in the sequential defend attack context. So that's initially that's the template that we are gonna discuss. So basically, there is a defender which is deploying defense. In our case, it would be the machine learning system that is deployed by an organization. In this case, the attacker sees the machine learning system, observes the machine learning system that is being deployed by the defender. The attacker launches an attack, and there is some result, which is theta. And taking into account the decision implemented and the result, the defender gets a utility, and the attacker, and taking into account his attack and the result, the attacker gets a utility. Before going ahead and explain how we solve this, first, you might think that this is a pretty strong formulation, because we are saying that the attacker is seeing the defense. That this is what is called in the machine learning in the adversarial machine learning literature, what is called a black box attack. But we have versions for more what is called gray box and white box attacks, right? So, because it's easier, I'm just explaining this, or I'm just sketching the solution of this. Okay, so what's our solution? The solution of this is we deal with the defender problem, right? Which is like this. It's the same. Now we have an answer. We have as a new uncertainty, as an additional uncertainty, which has been the action of the attacker. For this, basically, we need the utility, some utilities and probabilities. So basically, we compute what would be the expected utility if we implement a defense and a certain attack, right? Then we, given that we make a forecast of what would be the attack given our defense, we can compute the expected utility of each defense, and then finally we can compute the maximum expected utility. So you can see again optimization or maximization in machine learning. Now the crucial element, of course, is trying to forecast what would be the attack given our defense. Okay, and to come out with this, what we use is the attacker. What would be the attacker problem? The attacker problem requires, because we have no access to it, it requires us to come out with we model our uncertainty about the attacker preferences with what is called random utilities. And we model our uncertainties about the uncertainties of the attacker with random probabilities. As a consequence, we use random expected utilities. Here I have instanced this random depending on the corresponding atomic element. And as a consequence, I can compute the random optimal alternative, which is reflected there. And then we have that the required distribution, which was this P of D over A given D, can be defined based on this random optimal distribution. So basically, that's what we aim at doing. Sorry. Now this can be reflected as quite easily as a Monte Carlo scheme, and I've reflected it there. No interest in. I mean, that's okay. But we can also introduce an augmented probability simulation for adversarial risk analysis. If we go back, you can see that we are maximizing this expected utility here, and we are maximizing this random expected utility here. So that's where we can introduce our augmented probability distributions. In the cases, random augmented probability distributions given a D, and this would be this other random. This would be the other augmented probability distributions. And once based on this, we can basically we could consider like 2 stages, right? And we would simulate. We would try to simulate from these distributions. Okay. Now, as I said, to simulate with this, we can use, for example, we can use how do you say, Markov chain Monte Carlo, and I put here a Metropolis hastings scheme for this. You can see that there's two, what we call an outer APS and inner APS, but this basically defines a Markov chain which allows us to find the optimal defense for the for the machine learning system. We have theorems like I don't know, under certain good conditions, this defines some. Basically, it's saying that under certain good conditions, this defines a Markov chain who's with the required stationary distribution, and a consistent mode estimator based on marginal samples provides the optimal solution. This is a brief comparison in a simple example between to check that Monte Carlo and APS gives the same type of solutions. And this is a more interesting comparison from a computational point of view, and explains why this might be a why this is a super promising approach to the problem. I'm putting here the number of samples that need to be generated through Monte Carlo and through augmented probability simulation. I put here two cases. Complete would be the typical domain in game theory, and incomplete would be the kind of I mean, when there is no common knowledge, right? So that would be the case that I've been describing right now. But I just, for completeness, I put the other case. And you can see basically Q and P is the required sample sizes for the required precision, and then for MC, and then M are the required sample sizes for augmented probability simulation. And you can see here that there is the cardinal of D. That's the cardinal of the number of alternatives available for the defender, and this is the cardinal of A, which is the number of available alternatives for the attacker. The most important thing is, these are some formulas, just a bunch of formulas, but the most important thing is that the APS is not dependent on these cardinals, whereas in Monte Carlo it does. So this means that for very large problems, APS will beat Monte Carlo and will be a very, and for continuous, we will need to discretize, and given the precision, I mean, APS will definitely improve Monte Carlo. Okay, the interesting part of this is basically just the last column, and you can see when we require not much precision, Monte Carlo goes better than APS, so you can compare the 0.007 with this. But if we increase the precision, you can see that APS scales much better. So if we move from precision 0.1 to 0.01 in the results, the Monte Carlo timings multiplies a lot, whereas the APS scales much better. And if we go to 0.0001, basically with Monte Carlo we cannot do, but with APS we still get solutions. We can do in realistic examples. This is a sort of version of a real example, cybersecurity example that we did in another project. I mean, to compare, that was the template. In a realistic example, there's much more uncertainties, etc. And we can get results. That was a sort of maxima example, but we can get results. You can see that I mean, you could think that there is a pretty flat maxima in this case, but we have the good thing is that we have tricks to what we call pick the utilities, and so as to much better identify the optimal thing. And also for the same price, we can get very interesting with no additional cost. We get pretty nice sensitivity analysis results, but well, you can read it in the papers. And coming to an end, Basically, the thing says I've been talking about AML, which is basically machine learning perturbed by adversaries. I mentioned that it's traditionally treated from a game theoretical perspective, and this requires common knowledge, which is not very relevant in security. As an alternative, I've given approaches to mitigate this through adversarial risk analysis. But we are still in a point of time in which we can do backend applications, but not front-end applications. And as a consequence, it has been this new use of a methodology of augmented probability simulation. So there's many challenges. I don't know. It could go from from more theoretical. For example, developing an adversarial statistical decision theory which provides foundations to this. Methods in multi-agent reinforcement learning, that's quite important because it promises an approach to general artificial intelligence and the provision of efficient computational schemes. And what I talk today is an attempt to do this, and of course providing computation impairments. And this has many interesting applications. Some of them I mentioned. This includes like fake news detection, malware detection, autonomous driving systems. I mentioned a little bit on the type of applications that we've been doing, and also we are doing with Caixa some examples on finance, which are in these problems we deal with problems in which the adversaries are either competitors or attackers. That's but the maths are basically the same. Here's some reference on various topics that I mentioned. And this some thank you for the sponsors from AXA, BBA, and Caixa, and the US Air Force and H2020. And finally, well, thank you to the organizers. And if anyone is interested in this kind of topics, we would be. I mean, there's many problems to be solved, and we would be happy to share them. And thank you again.
Thank you very much, David, for your very interesting presentation, combining several areas. Thank you so much. We open the floor for questions, and remember, if you have a question, please raise your hand and we will unmute you, and you will be also able to ask the question yourself. Yes, so there is a question from Alberto. So you will be given the rights to share your screen and ask the question yourself. Yes, you can talk about. Yeah. You should be able.
Okay. Do you hear me? Do you hear me now?
Yes.
Yes, we hear you.
Okay. In first place, it's been such a great seminar. I really loved and interested in the topic. And the question that I have is that if the attacker could launch an attack that ends up in a different class that the defender has never seen. I mean, do the spaces of classes from the attacker and the defender be equal, or could they be somehow different?
I mean, they could. I mean, they could be different, right? Because they have different interests. But you could. I mean, you could define a super set that includes both classes, right? and then with some little work, you could define the utilities of both the attacker and defender based on those new set of classes. But yeah, they could be different in principle. Yeah.
It will be understood somehow like a surprise, right? Or unexpected attack or something like that.
Yeah, but that's different. That's I mean, that will be more basic in the sense of or more structural or more fundamental. What you're trying to say is that the that would be like that will be more not the classes, but the attacks available to the attacker. Okay, so that's what Donald Rumsfeld called the unknown unknowns, right?
Okay.
Yeah. So to deal with this, you could introduce some kind of attack which is a known attack or something like that, and trying to come out with some kind of model for this.
Okay.
Yeah, but that would be like more structural, and that's a very important issue. And by the way, yeah.
So thank you so much.
Thank you, Alberto. Is there any other question from the audience? I think it's all yeah,
Okay.
clear. Okay. Thank you very much for making time today. And yes, I would like to also make a small announcement to the public, yeah, if you don't mind.
Yeah, sure.
So for more than a year, we have had Sinia helping us with the online seminar series, and she is going on maternity leave starting tomorrow. And we would like to thank her for sending timely all these emails to the big mailing list that we have, uploading videos, taking care of the young online seminar, and many other things together with Christina. So thank you very much, Sinia.
Thank you. Thank you to you for this opportunity, Dolores and Emilia. It's a great pleasure to work with such people as you. Thank you.
And congratulations.
Thank you. And thank you to all speakers. It was wonderful and very interesting. So sometimes I rewatch the seminars because, yeah, it's a lot of information, and it's glad that we have it.
Thank you, Sinia, very much. Thank you.
Yeah.
And
Okay.
David, as I said, the video will be watched on YouTube in our 2 channels. So I'm sure that you will have a lot of views about this very timely topic and very interesting. Thank you so much.
Okay. Thank you. Bye. Thanks to everybody, and see you soon.
Thank you, everybody,
Bye-bye.
and see you everybody next week with the next speaker. Bye-bye.
Bye.
Bye. Thank you.